Welcome to Mythosium, the channel that turns complex science into simple, powerful ideas. Here, we take things you thought you understood and reveal the hidden truths behind them, one myth at a time. Today, we're uncovering one of the biggest misconceptions in modern science, how electricity really flows. Most of us were taught that electricity is just electrons traveling through a wire, little charged particles moving from a battery or power plant to your device, powering it along the way. But that simple picture, as neat as it sounds, is wrong. So what's actually happening? Let's start with a thought experiment. Imagine you have a giant circuit, a battery, a switch, a light bulb, and two extremely long wires, each about 300,000 kilometers long. That's the distance light travels in 1 second. Now, picture those wires stretching halfway to the moon and back. The light bulb is right next to the battery, just 1 meter away. Here's the question. If you close the switch, how long will it take for the light bulb to turn on? Half a second? 1 second? 2 seconds? Or instantly? Most people imagine electricity as a kind of fluid, that when you close the switch, electrons start flowing down the wire from the battery and eventually reach the bulb. So it must take at least a second for the electrons to travel that enormous distance, right? Actually, no. The light bulb turns on almost instantly, in just a few billionths of a second. How can that be? The secret lies in how electrical energy truly moves, not inside the wires, but around them. When you connect a battery to a circuit, it creates an electric field throughout the wires almost instantly, at nearly the speed of light. This field pushes on the electrons in the wire, causing them to drift slowly in one direction. But slowly is the key word. Their drift speed is only about 1/10 of a millimeter per second. So if electrons themselves are barely moving, how does the energy from the battery reach the light bulb so fast? To understand that, we have to look at what's happening outside the wire, in the invisible space around it. Every current-carrying wire produces a magnetic field, and every voltage difference creates an electric field. Where those two fields exist together, energy flows through the surrounding space. In the 1800s, Scottish physicist James Clerk Maxwell discovered that light itself is made of oscillating electric and magnetic fields. These fields move together, perpendicular to each other, carrying energy forward through space. A few decades later, physicist John Henry Poynting figured out how to describe that flow of energy. Mathematically, he defined what we now call the Poynting vector, which shows both the direction and magnitude of energy flow in electromagnetic fields. Here's what it means in plain English. Whenever there's an electric field and a magnetic field crossing each other, energy flows in a direction perpendicular to both, and that's how it moves from one place to another. So, what does this have to do with our light bulb? When you close the circuit, the battery's electric field extends through the space around the wires. The moving electrons in the wire create a magnetic field. Together, these fields form a channel through which energy flows, not inside the wire, but around it through the surrounding electromagnetic field. That's the real path energy takes. From the battery, through the space around the wires, and into the bulb. If you apply the Right-hand rule, electric field in one direction, magnetic field in another, your thumb points in the direction of energy flow. Around the battery, that direction points outward. Along the wires, it flows toward the bulb. And at the light bulb, it converges inward, delivering energy into the filament. The bulb glows not because electrons have traveled from one end of the wire to the other, but because electromagnetic energy carried in the surrounding space has reached it almost instantly. This may sound counterintuitive, because for decades we've been taught that electricity flows inside wires, like water through a pipe. But that's not what actually happens. Inside the wire, electrons hardly move. They simply vibrate slightly, or drift slowly under the influence of the electric field. The real action is in the invisible fields outside. The wire's job is not to carry energy, it's to guide it. The wire shapes the path of the electromagnetic field like a rail guiding a train. Think of it this way. When you turn on a light, you're not waiting for electrons to travel from the power plant to your home. Instead, the power station sets up oscillating electric and magnetic fields that extend through the grid at nearly the speed of light. These fields carry energy through the space around the wires, all the way to your home. That's why when you flip a switch, the LEDs respond almost instantly. So why doesn't the energy flow both ways if the current reverses direction? In alternating current, AC, the electrons in the wire simply wiggle back and forth. They don't travel miles down the line. But because the electric and magnetic fields flip direction together, the Poynting vector, which represents the direction of energy flow, always points from the power source to the device. Even when the current changes direction, the energy flow stays consistent. That's the deep insight. The electricity that powers your home isn't a stream of electrons from a power plant. It's electromagnetic energy traveling through the space around the power lines, guided by them. This discovery wasn't just theoretical, it solved real-world engineering problems. In the 19th century, when the first transatlantic telegraph cables were laid, messages couldn't travel clearly across the ocean. The signals distorted and slowed down. Some scientists thought electricity moved through the wire like water through a hose. But that idea didn't fit the data. Eventually, engineers realized that it was the field surrounding the wire that carried the information of inner electrons themselves. That's why power lines are built high above the ground, to reduce interference from the earth, which can conduct electricity and distort the surrounding electromagnetic fields. The air between the wires and the ground acts as insulation, allowing energy to flow cleanly through the fields around the cables. It's also why transformers, the devices that step up or step down voltage, don't rely on continuous physical connections. They use electromagnetic fields to transfer energy from one coil to another with no direct electrical contact. Everywhere in our power grid, from generators to homes, it's not the electrons doing the work, it's the fields. Let's return to that question from the beginning. When you close the switch on our imaginary 1 light-second long circuit, how long does it take for the bulb to light up? The correct answer is almost instantly, roughly 1 divided by the speed of light seconds, or about a few nanoseconds. Because the electric field propagates at light speed, the energy reaches the bulb not through the wire's length, but through the space around it. A direct path that's only a meter long. The bulb doesn't need to wait for electrons to arrive. The electromagnetic field carries energy to it nearly instantaneously. Understanding this completely changes the way we think about electricity. It means that energy doesn't live inside the wire, it flows around it. The wires are simply a boundary that shapes and contains that energy flow. When you power a device, the electrons inside the wire move back and forth slightly, creating and responding to electric and magnetic fields. Those fields carry energy through the surrounding space and into your device, where it's transformed into heat, light, or motion. So next time you flip a switch, remember, what powers your light isn't a flood of electrons traveling from some distant plant. It's an invisible wave of electromagnetic energy, racing through space at the speed of light, guided by the simple copper lines in your walls. That's the true beauty of electricity. And it's one of those ideas that's so simple once you see it, yet so deeply misunderstood that it changes how you think about power, light, and the nature of energy itself. At Mythosium, we love uncovering these hidden truths, the kind of insights that make you see everyday science with fresh eyes. Because the world around us isn't just full of technology, it's full of wonder, waiting to be understood. If you enjoyed this exploration into the real nature of electricity, make sure to subscribe to Mythosium for more stories that transform the complex into the clear. Thanks for watching. And next time you switch on a light, remember, the real magic isn't in the wire. It's in the space around it.